Okay, then let's start. Welcome everyone. We have quite a big audience, an international one as well, which is great. So today's talk in DutchCATS is going to be given by Andrew Swan from Carnegie Mellon, and he's going to talk about definable and non-definable notions of structure. So maybe first a bit about DutchCATS. I mean, we started a bit during the pandemic, where there was not a lot going on, and maybe so there were some people. I think maybe I just wanted to show also maybe to the students that there are people interested in type theory and category theory in the Netherlands, and so I'm hoping that it still has this function that to bring some people interested in these topics, especially in the Netherlands, together. But people from all over the world are welcome, and it's great that they're here. So first, maybe one question is: can people just interrupt you with questions, Andrew? Or
yeah, sure.
Okay,
that's fine.
Cool. So the talk will be like 1 hour. I mean, we're quite informal and flexible. So please interrupt Andrew if you have some question. And yeah, okay, take it away.
Thank you. Yeah. Okay. So so this talk is about definable and non-definable notions of structure, and these are notions of structure on a fibration. So I guess I wanted to kind of start by kind of saying why I like fibrations. So I ended up writing a bit of an essay about this in the abstract, but I guess the short version of why fibrations are cool is that in naive category theory, we often make a kind of implicit reference to sets, and thereby to set theory. So, just some examples. We talk about Hom sets, sets of morphisms. We talk about small limits and co-limits. So we need, set-sized diagrams to talk about these things. In a kind of classical result of the adjoint functor theorem, it takes as an input, it takes a solution set condition. Okay. And so my own motivation for kind of using fibrations in my work is from homotopical algebra, where we have these things called weak factorization systems, and then some of these weak factorization systems have the property of being cofibrantly generated. And so cofibrantly generated, this is something else which makes reference to sets. So a weak factorization system is cofibrantly generated if it's generated by a set of okay. I guess I'm not going to define this, but it's generated by a set of left maps, if you like. Okay, so yeah, so one of the reasons why people study the fibrations and why I study fibrations is to kind of break this dependence on set theory. So I think, yeah, okay, here's an extra bit. So in topos theory, we often want to think about a topos as a kind of universe where we can carry out mathematics, and so this could be the category of sets. That's a topos, but there are kind of lots of other examples. So a lot of the examples I like come from realizability, and so in this case, I guess one way of thinking about this is you have, instead of having sets, you have sets with like little natural number labels on them, and then you can talk about not just functions, but functions which are computable in the sense that you have a way to compute the output, natural number label from the input in some sense. Yeah, so it's what if you want to do mathematics in the internal logic of such a topos. then you probably want to use that instead of the category of sets. Okay, and okay, yeah, and so we can just kind of directly use the internal logic of a topos, but then the problem is it's kind of limited in that the internal language of a topos only talks about things inside the topos. Whereas if you look at these examples, we have kind of two categories hanging around. So, so we have the category of sets, which is like our topos, and then we have another category which might be locally small, or it might be complete or code complete. And so you kind of need a way to talk about another category in the internal language of a topos. And so this is kind of one way, I guess, kind of the main way to motivate vibrations. So yeah, so we think, so the idea of a Grothendieck vibration is we have a functor from, so let's say a functor from E to B, and we say that B is the base of the vibration. So this is kind of a foundation, a kind of topos where you want to do a kind of internal language stuff and interpret mathematics into a topos B. And we think of E as a way to talk about kind of families of objects indexed by B. So yeah, so the idea is if we have an object I of B, then we think of this as like an indexing object for a family of objects. So maybe think of it as like an indexing set, for example. And then things in the fiber of I, we think of the set of, we think of it as a category of families of things indexed by I. And okay, and then we also need a notion of morphism, and we take, and for morphisms we use what are called vertical maps. So a map is vertical if it's sent to an identity map by this functor Q. And of course we can take this, and this is a kind of intuitive picture that we think of I as an indexing set, and there's an element of EI as being a family indexed by I, so something of the form xi I and I in a set theoretic notation. And so this is always a useful picture, and we can also make this literally true by taking B to be the category of sets, and yeah, just taking E to be the set of these set index families of objects. So these xi, these would belong to some category C that we want to kind of talk about. Okay, and okay, so that's a kind of basic idea, but it turns out that for this idea of indexing objects to work, we need one more thing, and that kind of one more thing is a way to re-index families of maps. So in this example, set index family, if we have a family of things indexed by I and a function from j to I, then we can turn it into a set indexed by j just by having the same objects, but just composing it with this map sigma, if you like. So this is a kind of re-indexing it to get a family of things over j rather than the family of things over I. And so this is formalized. So I think this definition was originally due to Grothendieck, and it's kind of, and it's formalized using Cartesian maps and Grothendieck vibrations. So so we say a map is Cartesian if whenever we have a diagram like this, like the solid lines in this diagram, there's a unique map T here. So if you like, this is a kind of universal property that's satisfied by the by this re-indexing here. Okay, and then a growth and decay fibration just says that for every object X of, so this E is called the total category. So for every object X of the total category, every map sigma from I into the indexing object for X, we can find an object sigma star X. So this is the, I like to call this a re-indexing of X, and a Cartesian map from the re-indexing to X that kind of witnesses that it is a re-indexing, if you like. So that's a kind of very, very quick introduction to fibrations. So hopefully I didn't spend too long on that. Okay, so now what do I mean by notion of structure? Yeah, so this is a, so this is some kind of variant of a definition by Mike Schulman. So if I write, Schulman here. So he gave a definition called a notion of fibered notion of structure. So this is some kind of variant of Mike Schulman's definition of fibered notion of structure. And then so the idea is if an object is if an object in the total category is a family of objects, then what does it mean to have some kind of structure on these objects? So for example, if we have some kind of family of sets, then we could have a group structure on each set. So that's one example of structure. So that's an example of a monadic notion of structure as I defined later. But it can be something more general. So so we can kind of see properties of an object as a kind of special degenerate case of structure by looking at the kind of special case when an object has at most one structure. So we can think of that as a property. So these are called full notions of structure. Yeah, and I I'll talk about those, and there's also one more example, but I'll just show you the example when I come to it. But yeah, so for now, I just kind of say the definition. So the definition is, so we have a fibration from E to B, brief and deep fibration, and then a notion of structure is another category together, such that together with a functor chi from D to E. So by fibered functor, I mean that it commutes with the fibrations and it preserves Cartesian maps. So so I kind of say fiber to me preserves Cartesian maps here. And because of this, it restricts to the wide subcategories of C and D of just the Cartesian maps. So yeah, so in other words, we just keep these re-indexing, and then we throw away the vertical map. So you throw away the notion of morphism, if you like. And yeah, and then so then this is, and then a notion of structure is when this restriction to Cartesian maps is a discrete fibration. So then discrete fibration says that whenever we have a yeah, okay. So I guess what this is saying is we have our family of objects, xi, and then we index this along some map from j to I. Okay, and yeah, okay, and right, and then so then we have a structure on xi. So maybe a kind of a group theoretic structure, if you like. Okay, and okay, yeah. So either So for example, these could be sets, and then a group structure on the set, and then given this kind of re-indexing from, so we have x, xj, j in, so x of sigma j, j and j in the Cartesian map. And then you have a unique way to take the group structures on here and then view them as group structures on here. So I guess in the set index family case, it's kind of trivial because it's just kind of taking the group structures here and just it's the same thing on here. Okay. So this is just a kind of a very kind of succinct way to kind of identify a key property of this idea, and but the intuitive picture is that the objects in the fiber of X in E is a structure on is a collection of structures on X, and then we can also think of the maps in D as being homomorphisms, if you like. So yeah, so I mean, again, another thing I can say is that if you have a group structure on here, there's a unique group structure on these guys that makes this Cartesian, this re-indexing into a group homomorphism, if you like. So that's the intuitive picture. Okay, and right, and then so amongst notions of structure, we can talk about the definable ones. Okay, so this is kind of equivalent to what Mike Schulman called local representability, but I'm going to kind of try out a different name. So I kind of see this as a kind of generalization of a definition by Benabou, and in the same kind of spirit as Benabou's definition. So I'm going to refer to this as definable, and so a notion of structure is definable just if this restriction to Cartesian maps has a right adjoint. Okay, and so we can also formulate this definition of definability using representability of pre-sheaves. So if we have any object X in E, so a family of objects in our total category, then we can define a pre-sheaf on the slice category of B over the indexing object for X. And what this pre-sheaf does is it takes a map I into the indexing object for X and then sends it to the collection of objects in the fiber of the re-indexing of X. Okay, and then chi is definable if and only if this chi X is representable. So the way to think about this is that we can talk about these structures in the internal logic of the base. Okay, so a representing object of a pre-sheaf like this is in particular an object of this category. So it's so an object of this slice category, B over Q of X, and so we can think of it as a way to talk about the notion of structure in the internal logic of the base B. So so yeah, so that's a kind of way to think about this. Okay. Yeah, so here's a first example. So yeah, so as I said, the we have kind of property as a kind of degenerate kind of structure when every object has at most one structure. So yeah, so it's Mike Schulman called these full notions, fiber notions of structure. So I do as well. And so yeah, and yeah, so another way to think about this is that we have a class of objects which are closed under Cartesian maps, so closed under reindexing. So if X has some property of belonging to D, then Y also has this property, and F is a Cartesian map, then Y also has the same property belonging to D. And so then this inclusion of a full subcategory is what we call a full notional structure. Yeah, okay, in this case, yeah, so in this case, the representing map, so yeah, so phrase things in terms of, so phrasing definability in terms of representability of these pre-sheaves. So for the full notions of structure, this pre-sheaf is subterminal, and the Yoneda embedding reflects subterminal objects. And so this tells us that our representing map into Q of X has to be monomorphism as a mapping. So the kind of way that we think about this is, maybe I even wrote this. Yeah, okay. So yeah, so this kind of typical example is like how we think about it. Yeah, so we have our family of set index family xi here, and we actually have a class of objects in our original category C here. So I guess in so for illustration, I'm kind of I guess I'm restricting to the special case of set index families here. So a total category is a category of set index families, and then it's in this example it's indexed over sets. Okay. Yeah, and so in this case we actually have our class of objects in our category C, and then we can make this into a full notional structure on these families here. And then we say that this family of objects belongs to D tilde whenever every object in the family belongs to D. And so this is always definable, assuming full separation. And it's definable, and we know it has to be definable by a subset of I, because the representing object is a monomorphism, and it's by this subobject. It's just those I in the indexing object, such that xi belongs to our class D here. Okay. So that's kind of typical picture to kind of keep in mind for so for full notions of structure. Yeah, but yeah, so here's another example where we can see kind of a bit better why you might call this kind of thing why you might call this kind of thing definability. And yeah, okay. There's kind of another very important example of fibrations. I don't think I mentioned yet, so I'll mention it now. And this is codomain fibrations. So in a codomain fibration, so in a kind of set index family fibration, we had a category C that we're interested in and want to reason about it with sets. And with codomain fibrations, we have a category B, so maybe a kind of a topos or something, which has a nice internal language. And then the codomain fibration is a way for B to talk about itself, if you like. So, so if we have I in B, then in the internal language of B, we can think about a family of objects indexed by I just as a map from X to I. And in this case, the reindexing is given by just given by pullbacks, because that's how the internal logic works. Okay, and yeah, and then so for any fibration, we can define a class of subterminal objects. So let's, for convenience, assume that we actually have terminal objects in this fibration. And then the subterminal ones just those objects for which the unique map into the terminal object is a monomorphism. Okay, so this always gives us a notion or a full notion of structure on the fibration, and it may or may not be definable. So now in an interesting special case of codomain fibrations on a heighting category, it is definable. And the reason is we can define this property of being subterminal in the internal language of the heighting category. So, so an object is subterminal if any two of its elements are equal. So, so I guess in homotopy type theory, these would be called propositions or H propositions. And yeah, and then so we can do this in our heighting category. And so here we're really using the internal logic to define this class of objects. Yeah, and then so the representability is saying that this kind of internal definition matches up exactly with the external one as subterminal objects. Okay, so that's the full, and yeah, so there's a lot of examples of non-full examples of notions of structure, and unfortunately I don't have time to go through a lot of them, but I will talk about the most important example of notion of structure, and this is notion of structure of vertical maps. So if we have a fibration E to B, E over B, we can define a new notion, a new fibration, which consists of pairs of families of objects over the same indexing set. So in set index families, it'd be something like xi, yi, where I and I. So that's just the illustration for set index families. So okay, so we can define a fibration here, and then we can define a notion of structure on this fibration of pairs of objects. Okay, so what is a structure? Well, a structure on a pair of objects is just a vertical map from X to Y. So I think this is maybe a good chance to introduce some notation I'm going to refer to later. So I write vertical maps as VE. So this is the fibration over B, and then we have a map from VE to E times E over B, and so the elements of this guy are the vertical maps in E. Those are the objects with morphisms commutative squares, and then we have, given a vertical map, we can just look at its domain and codomain to get a fibered functor into E times E. Okay, and oh yeah, and this is an example of something more general that Peter Johnson called a comprehension scheme. Okay, so we say that, oh, okay, right. So this is not always definable, but if it is, we say that the fibration is locally small. So, we say that Q is locally small if how can I write this? I just call this chi. If chi is definable. Okay. So this is so local smallness is saying that we have a way to talk about maps between objects of E in the internal language of B. And so this is very important because once we can talk about maps, then we can start doing category theory, and then there's like all kinds of other stuff that we can define using the category theory. And there's a kind of a bit of notation here. So I write the representing object as hom I xy, and yeah, and so something interesting about this local smallness is it can look very different depending on which particular Grothendieck fibration we are working over. So for set index family fibrations, it is just the co-product of hom sets. So yeah, so if you have two set index families here, then we have a hom set from each xi to yi, and then yeah, and then hom I is hom I is just a co-product of all of these hom sets. However, for codomain fibrations, it looks very different. So in this case, it's still locally small as long as the category B here is locally Cartesian closed. So yeah, so maybe a better way of phrasing this is that these so the kind of pre-sheaves, so these kind of pre-sheaves chi xy, these are representable precisely when the they are exactly the exponential in the slice category B over I. Okay, so in particular, if they exist, then the slice category has exponentials and vice versa. And then so as a corollary of this, a codomain fibration is locally small if and only if its base B is locally Cartesian closed. Okay, yeah, so a kind of important point, which is maybe forgot to emphasize, is that definability is really a property rather than its definability is unique because writer joints are unique up to isomorphism, and also looking at it this way, representable objects, the representing object is unique up to isomorphism. So so like with any kind of definability, these hom objects are uniquely defined, uniquely determined up to isomorphism by the fibration where we're working. And it just happens that we have these kind of nice description both in set index family fibrations and in codomain fibrations. But so these kind of look very different, but they're still hom objects in a locally small fibration. Okay, and then a final class of examples. So I guess I'll go through this kind of quite quickly, but for me, this is kind of the main source of examples, which are what you might call algebraic examples. So if you have a functor over a fibration, so I just mean a functor which commutes with the fibration, I guess this should be Q if this is a Q here, such that it commutes with Q and T commute, but T doesn't have to preserve Cartesian maps. And if it does preserve Cartesian maps, I say it's fibered, but it doesn't have to in general. And kind of similarly, and then we can also define pointed endofunctors, which have a unit natural transformation here, or monads over B, which have a unit and a multiplication. And then we can use this to define algebra structures. So yeah, so if you have an object X of E, then an algebra structure is a vertical map from T of X to X. And Oh, and of course, if T is a pointed endofunctor, then algebra should be compatible with the unit. And if T is a monad, then the algebra should be compatible with unit and multiplication as well. Okay, and then so this defines a forgetful functor, and this always gives a notional structure on the fibration E, and it may or may not be definable. Oh yeah, so sometimes it is. Oh, okay, yeah. So this is what I just said, that it always gives a notion of structure, and in a certain case, so if T is a fibered, so if it preserves Cartesian maps, and the fibration is locally small, and B has finite limits, then the algebra structures are definable, because we can, because an algebra structure is just a homomorphism, and once we can talk about homomorphisms in the internal language of B, then we can talk about the algebra structures too. Yeah, so I refer to notions of structure of this form as monadic, and I just emphasize again that T doesn't have to preserve Cartesian maps. Okay. And then so an important special case of this is algebraic root factorization systems. So I guess this was like my original motivation for looking at these guys. So an algebraic root factorization system. So this is not quite the usual definition, but it's equivalent to the usual definition by a theorem of John Bork and Richard Garner. And I'm just going to take it as a definition today. And so an algebraic root factorization system is a monadic notion of structure on a codomain fibration, together with some kind of composition functor that makes this T algebra into a double category and chi into a double functor. Okay, so an algebraic root factorization system is just a monadic notion of structure on a codomain fibration with this extra composition functor. That so I think of this as a kind of algebraic version sigma types. So it's so we can also think of these guys as comprehension categories, and in this case, composition is like a sigma type in the comprehension category, together with an extra strictly associative and yeah, so it's kind of like a sigma types which have the extra property of being strictly associative and having strict identities. And then we can generalize. Yeah, okay. So this definition here is like specific to a codomain fibration, but we can also do a kind of internal version of this, by which I mean kind of internal to another fibration. So if we have some fibration E over B, then we can think of this vertical map fibration that I mentioned earlier as a kind of internal version of the codomain fibration. So so this gives us a composition of two fibrations. So we have B, E to B, and this goes down to B. And okay, well, okay, I guess there's also a domain as well, but let's take the codomain because that's what happens with the definition here. And yeah, and then so we can think of this codomain fibration on the vertical maps as a kind of internal version of the codomain fibration to this kind of original fibration Q that we're kind of interested in. And then so we can use this to give an internal version of algebraic root factorization system. So so I'll say that an algebraic root factorization system over a fibration is a monadic notion of structure on this kind of internal codomain fibration. And yeah, and then it needs to be monadic, and it should also have a composition operator, just like with the original definition of algebraic root factorization system. And then I say it's fibered if it preserves maps that are Cartesian over B. And yes, so when we have a composition of two fibrations like this, and we have two different notions of Cartesian map up here, depending on whether we're thinking of this as the base of the fibration or this as the base of the fibration. So fibered is when we take this as the base of the fibration. So fibered algebraic factorization preserves maps that are Cartesian over B. And then strongly fibered, this says that we are thinking of E as the base of the fibration. So in this case, P has to preserve maps that are Cartesian over E. So we're thinking then of this as the base. And then we can, yeah, so it turns out that this one is a quite a strong condition. So it holds in some useful special cases, but it's not, there's like loads and loads of natural examples where it doesn't hold. Whereas this one turns out to be reasonable. Like this one holds in most examples. So I kind of focus on this definition. And yeah, and then so we can also think of a fibered algebraic refactorization system as being an algebraic refactorization system on each fiber category EI, such that the monad is preserved by re-indexing along maps from J to I in the base B. So it's kind of, yeah. Okay. So kind of related to algebraic refactorization systems, we can also define a kind of notional structure called lifting notional structure. So this is again something which is defined over the codomain, this kind of internal codomain fibration, VE on vertical maps, VE through E. And so given a vertical map F, so we fix a vertical map M to generate the lifting structure, lifting notional structure, and then given another vertical map F, a lifting structure on F is some kind of coherent choice of these dotted diagonal maps here in every commutative square of this form. And I guess this should be like kind of coherent in some way. And yeah, and if this is a locally small fibration, then we can also phrase this as various different ways. So for example, we have a kind of canonical map here in B from, so if you like, this takes a diagonal map and then composes it with these guys to get a square. And it's a lifting structure is a section to this map. Oh yeah, so and then a kind of typical example is we might have an interval object in our terminal fiber, for example. And then we have this kind of special name for the fibration structure, which is Heurig's fibration structure. And there's also a more sophisticated version of this that I'm not going to have time for, but there's a more a fancier version of Heurig's fibration called Kahn fibration structure. But yeah, I'm not going to define that today. Yeah, so then every lifting notional structure has a composition functor, like in the definition of algebraic refactorization system. So a lifting notional structure is a fibered algebraic refactorization system, precisely if it's monadic. And yeah, so and then so we call algebraic refactorization systems of this form as cofinally generated. So that's just a name for them, if you like. And then under lots of reasonable conditions, we can take a lifting notional structure and show that it's monadic. So this is kind of the kind of classic version by Richard Garner. So the way I like to think about this is as something which lives over category index families fibration. I'm not sure if I mentioned those yet, actually, but just like with set index families, we can also have category index families. So So in this case, index and object is a small category, and then a family is a functor into this category C that we're actually interested in. Yeah, so I think of this theorem by Ushkan has been about kind of category index families, and it's showing that certain lifting notions of structure are monadic if C has certain properties, and then there's also a version of this for codomain fibrations that I did. There's actually two of these, but just put this one here just as an example. Yeah, so in one sense, we can kind of get a definability of algebraic refactorization systems for free from local smallness. And what this is if you have a locally small fibration, then any fibered algebraic refactorization system viewed as a notional structure on this kind of over the base B is definable. So that's kind of for free, but in practice that's not actually what we want. So as I said, this definability is equivalent to what Mike Schwarman called local representability, and he had a whole paper about showing constructing examples of showing that you can construct a certain define a certain locally representable notion structure, which is somehow equivalent to Kahn fibrations in some sense. But in that case, this kind of definability that we get for free is a wrong notion. Right? Like what we want is actually this kind of this alternative definition, which is in practice more difficult and like kind of harder to satisfy, which is what I'm going to call fiber-wise definability. So, so a lifting notion structure is fiber-wise definable if if the restriction to for each I, the restriction to I, so this is just an algebraic refactorization system on EI, if this is definable. Okay, so this is kind of yeah, yeah, this is harder to do, but there are examples where this holds. So for example, yeah, any strongly fibered algebraic refactorization system under certain conditions will be fiber-wise definable in this sense. And okay, so it's kind of right. So I'm starting to get to the kind of important things now, and so I guess there's kind of two things I wanted to talk about, and which I'll have time to quickly at least overview both of them. And the first of these is a kind of sufficient criterion for showing that a lifting notion structure is fiber-wise definable. So okay, so as I said, strongly fibered is kind of quite a very strong condition. So it holds in like a few special cases, but like there's loads of examples where it doesn't hold. So yeah, so I guess the first thing is a criterion which holds more often, and which is kind of easier to get in more examples for showing that a fibered algebraic factorization system, not necessarily strongly fibered, is fiber-wise definable. And then so this uses a definition called tininess. Okay, so this is a generalization of kind of some existing notions, but point out that this is something which is defined for families of objects, and it's something which holds in you can define in any locally small fibration, and it's defined using the hom objects in the fibration. So as I said, like in any locally small fibration, these are uniquely defined optoisomorphism, but they can look very different depending on which fibration we're working in. So maybe we're working over set index families, and then this would be a family a coproduct over the hom sets, or we might be working over codomain fibrations, and then it's completely different. Then it's a local exponential in the slice category. This definition is something which makes sense in the full generality of locally small fibrations. And it just says that this kind of certain functor, so for every j, this functor from the fiber category EJ to this size category in B has a right adjoint. Okay, so this is a family, what it means for a family of objects to be tiny. Okay. So for example, a set index family of objects is tiny precisely if each home set functor, so this would be for each xi, the home set functor has a right adjoint. So under like, if we're working a category which is locally presentable, this is the same as this home set functor preserving colimits. And then in the pre-sheaf category, any representable object satisfies this condition. Okay. What do I have next? Oh, okay. Okay. In over codomain fibrations, it's a different story. So in this case, well, we can phrase it using dependent products like this. So this kind of dependent product functor between size categories. This has a right adjoint this is what it means for a map to be tiny. Okay, and again, we have a nice way to get some examples in pre-sheaf categories, but in this case, it's not representable objects that are important, but what are called representable maps. So a map is representable if whenever we pull back the map along something from a representable, then we get something which is also representable. So these representable maps are always tiny as families of objects in a pre-sheaf category. And as a special case of this, we might have a family of one object. So this is a map into the terminal object. If this is representable, then this is a kind of tiny family of one object, or just a tiny object, if you like. So this kind of recovers the kind of existing definition. And just as a warning, hopefully I have very quickly mentioned why this is important, but it can happen that for representable objects YD, the unique map is not representable. So sometimes it is. So if products exist in our small category C that we're taking pre-sheaves over, then this will be a representable map when this object is representable. But it's not always true. So that's kind of an important point. Okay, and then I'll skip over this. I'll skip over this as well. So then the theorem is that if you have a family of maps with a tiny codomain, and this kind of dependent product conditions applies for our fibration for the base for B, then the lifting notional structure generated by M is fiberwise definable. Okay, so so we have this kind of funny condition about dependent products, and the way it's phrased like this is that, well, it applies for when B is locally Cartesian closed, but also these dependent products happen to exist, like these particular dependent products exist in CAT, in the category small categories, so the theorem also applies to category index family fibrations. Okay, so that's sufficient criterion for showing that lifting notional structure is definable. And okay, so unfortunately I won't have time to sketch a proof, but I will just very quickly just list these examples of non-definable notions of structure. So I guess kind of the key point for seeing why something is non-definable is that definability is actually a really strong property. So In particular, so one of the characterizations of definability is that this functor has a right adjoint, and yeah, and it turns out that the discrete fibrations always satisfy the necessary condition to apply Beck's monadicity theorem. So this has to be comonadic if it has a right adjoint, and right then comonadic functors create colimits. Okay, and skip over this. If we apply this to push-outs and codomain fibrations, and we can kind of explicitly read off what this is saying. It's saying that if we have, so if you have a cube here, where all the side faces are pullbacks, and then the top and bottom faces are push-outs, and if we're given structures on these three maps, so this map, on this map, this map, and this map, if we're given structures on these guys, then we can glue them together in a unique way, to get a structure on this guy. Okay. So this uniqueness is key, and it's just a corollary of comonadicity. It's just classic category theory. Yeah, so unfortunately I don't have time to sketch out proofs, but the simplest example is Hurwitz fibrations in topological spaces. Like, okay, I can't resist. I'm gonna sketch the proof. So if we have two okay, so if we think of this as a so if we think of this as a kind of map from R2 down to the line, well, okay, from a half of the real, from half of R2 down to the half of the real line, and if we have a kind of another fibration, which is another Hurwitz fibration, which is kind of the other half of the line, and the other half of the plane, then we can kind of glue them together to get the entire real line. So this is kind of, this real line is by gluing together these two pieces of the real line, and then you can get the whole of the real plane R2 by kind of gluing together two halves with a little bit of overlap here. And then if this was definable, which it's not, then we'd have a unique way to define a fibration structure on this half and this half to the whole thing. But we can't do that, because if we get a path from here, which kind of crosses over from one half to the other and doesn't strictly belong to either part, then there's like, then it's not specified by the existing fibration structures on this half or this half. So there's like a whole bunch of like different things that we can kind of take it to be that would all kind of witness this guy being a kind of vibration. So that's kind of very rough sketch, and it turns out that there's similar argument to this works whenever we have an interval with which admits a linear order. So this includes kind of special case of simplicial sets. So apparently this is kind of independently due to Christian Sattler, and yeah, so we can show that neither Kahn fibrations nor Hurwitz fibrations are definable in simplicial sets or any topos where the interval has a linear order. And so also there's kind of another example of what I call separable diagonal. So so a topos with an interval object, a separable diagonal with well, we can take this square and then kind of put away the diagonal. So take the diagonal part of the square here and kind of put it away from the square and treat it separately but it's not quite separate because it's still attached to this square at kind of two places at its endpoints. So that's kind of what this separable diagonal condition is showing. And this it's also possible to show that if we use this this interval to define Heurich vibrations or Kahn vibrations, then they're not definable. So neither of these are, neither Kahn vibrations nor Heurich vibrations are definable. And this applies to the kind of the first cubical set category that people considered in constructive models of type theory. So this is Besan, Kahn, and Tuba cubical sets. This kind of applies. Yeah. Okay. So that's a summary. So yeah, thanks for your attention.
Okay. Thank you very much. I'll do some applause. Right. Okay. I have some questions, but maybe some other people have questions as well. You know?
Thomas have a question?
Gonna mute yourself. Can't hear you yet. Thomas, I mean, oh.
You're on mute. Okay.
Remarked at the end that certain notions of homotopy some kind of vibrations are not definable. Is this a problem for anything? I mean, definability is an attractive notion, but for which purposes is it necessary, and for which purposes it's not so much of an issue? I mean, those models have been considered, and yeah, you see the point?
Oh, so you're asking why are we interested in definability?
No. I mean,
well,
I'm asking whether it's a problem if some notion of vibration is not definable.
Yeah, so I guess so the motivation I'm interested in, which is kind of the same as Mike Schulman, is in constructing models of homotopy type theory. Yeah. And so the way that you construct the universe, kind of following Mike's idea, is to take a the extensional model. So it's what we call the Hofmann-Streichen model universes in Preachute, and then we use definability to get the universe which classifies vibrations. And so the definability is saying that this kind of classification of vibrations is working the way that it should do. So if it's not definable, then I guess it doesn't necessarily mean that everything breaks, but it's kind of not working as well as it should do. So I guess there's kind of an extreme version of here in the BCH cubical sets, where I think in this case the universe of Kahn vibrations is not itself a Kahn vibration. So this is kind of a big problem. If you want to use this universe, you want to use this as a universe in the model of type theory, and it's not even a Kahn vibration, so you don't really have any hope of using it that way. Whereas when we have the definability, the universes are kind of working nicely. We have this kind of precise characterization of Kahn vibrations as classified by the pullback. Once we fix the map into the extensional universe.
Other questions? Maybe I can ask some questions as well. So Yeah, so I understand the role of definability also because I mean just for as a follow-up to Thomas's question, I mean because I mean yeah, so see how you want to use that in constructing universes in these different pre-sheaf models. But I mean you were also interested. I mean at one point you had this notion of fiberwise definability.
Yeah.
So what is the role of this notion of fiberwise import definability?
Okay, okay, where did I define it? Yeah. So as a special case of this, we can take I to be equal to 1.
Mm.
Okay, and then so this is what we're really interested in, right? This is the original algebraic weak factorization system that we're actually going to use in type theory. And it just happens that we can, if we're doing this for the terminal fiber, you might as well do it for the other fibers as well. It turns out to like not matter so much. I mean, I guess you kind of could use this in models of type theory, but I mean, I don't know if a very like a very persuasive reason to do this, but we could, for example, so in each EI, we have an algebraic weak factorization system, so we can also construct a universe in each EI. I mean, I don't know why you would do this, but it is something you can make sense of as in terms of models of type theory. I think the main reason is just that once you're doing something for the terminal fiber, you might as well do it for the other fibers as well. I just found it.
Okay, but even if you just stay this condition just for the terminal fiber,
yeah.
What does it add or say exactly?
Oh, okay. Yeah. Okay. So it turns out that if we just looking at the terminal fiber for definability, then we can also take the J here to be 1 as well. So I guess the I here is the same as the J here, if you like.
Okay.
I mean, in this case, it's saying we have a map from E1 to B over I, and it's just that this has a right adjoint.
Okay, but yeah.
I mean, I can kind of reformulate it in a codomain fibration. You can kind of reformulate it in terms of dependent product. So it's saying that this dependent product has a right adjoint.
Okay, but this is tininess. No, I mean, I'm getting confused now because I mean.
Yeah, this is tininess. Yeah.
Yeah. And but I was, I mean, but is this the same as fiberwise definability? Oh, sorry, I was asking about fiberwise definability, but is it?
Yeah. Okay. So for fiberwise definability,
Yeah.
you need this for every J.
Okay.
And it turns out that if instead of fiberwise definability, you could just look at I equals 1.
Okay.
Because that definitely is the case that we're interested in, because that's the original algebraic weak factorization system. Okay, so this is the one which is kind of directly used in the models of type theory. And it turns out that in that case, we can just take the J here to be equal to 1 as well.
Okay. But are you saying that this notion of fiberwise definability and this notion of tininess are in a way equivalent or
so that they're linked. So
they're linked, okay.
Yeah. So the tininess is used to prove definability.
Okay.
And it turns out that you can do this like one fiber at a time.
Right, but okay, but I was understanding this as okay. Okay, so I'm still a bit good at me. So I was trying to understand fiberwise definability, and okay, this theorem it sounds like you give tininess gives a sufficient condition for something being fiberwise definable, but I'm still unsure why you would be interested in fiberwise definability and Okay.
I mean, so do you agree that the case I equals 1 is
Yeah, no, okay.
yeah.
Yeah, I suppose, yes. I mean, I understand that you only want to construct a universe of the terminal object, yes. Yeah.
I mean, you just get the other fibers by the same argument. So you, because you get them for free, I just added them in, but
Sure.
they're not necessarily, this is not necessarily like a useful thing to do. It's just you get it for free by the same argument. Sure.
Okay. Okay. And then maybe another question I had was, so you had this definition of algebraic weak factorization systems in terms of what is it? Something indefinable. Yeah, this one. Yeah, this one. Right. So. So this is what they in the Burke and Carney paper they call the Beck's, maybe the Beck's theorem for algebraic weak factorization systems, or is that?
Yeah. So it's that kind of thing. So I think kind of technically it's one of the propositions they use in the proof of the.
Yeah. Oh,
Beck's theorem,
okay. Yeah.
it
I
is
mean,
argument.
yeah, they have some sufficient condition for. I don't know when this is called the concrete double categories of other categories of right algebras for algebraic weak factorization system.
I mean, in this formulation, the completeness is kind of hidden in the fact that it's a notional structure.
Yeah, and their conditions are sort of okay. So you already assume that it is monadic, and maybe somehow this is just an equivalent. Maybe so you're basically saying this is an equivalent definition of one of the propositions that they have. Yeah, okay, that's what I suspected. Okay, that is yeah. Okay. Okay. And I mean, so do you have these? I mean, the results that you have in the end, they're all sort of negative results, right? I mean, basically show that certain things are not definable. Or
once the end,
yeah. So, so what? So what does that mean for people who want? What is sort of the message that is for people who want to construct models of type theory? They there's, for example, is also particular implications for certain notions of cubical sets that are not.
Yeah. So
use certain variants of cubical sets as well.
Yes. So I guess it's oh, okay. Yeah. Yeah. So right. So the lesson with the cubical sets is that if we're working in BCH cubical sets, then we really want to use the built-in what I'd call separated products, so the monoidal products in BCH cubical sets, and don't use Cartesian product because this is what happens. But this is the only thing that goes wrong. Like other than this, you can do all the Autumn Pit stuff that works in BCH cubical sets fine. This is the only thing that fails if you use the Cartesian products in this category.
Yeah.
But this is kind of like a reason why actually you should be using the monoidal one. That is the correct one, not the Cartesian. So for simplicial sets, this is if you want to use this definition of current vibration over the interval. Then this is probably the wrong one for getting models of type theory. So I mean, as you say in your work with Eric, that you have this kind of other definition which is definable. So if you want to models of type theory, that'd be better than the kind of usual
Yeah,
definition.
yeah. So I mean, and here you say Kahn vibrations. But I think yeah. So but but you really mean uniform Kahn vibrations here, right? I mean,
Yeah, so I mean,
or this is it?
I mean, with respect to codomain vibration, visual sets. So
But I
it's
mean, but I mean, if you're, what is your definition of Kahn vibration here? I mean, is it?
yeah,
Is it just lifting property with respect to Horn inclusions, or is it something else?
oh, okay. So this is yeah. So I guess in general,
Yeah.
I mean that I think I mentioned it somewhere here. Oh, okay. Yeah, okay. I remember I didn't really define it properly, but if we have a great and deep vibration and it needs to object in the terminal fiber, then we can define here its vibration structure as in terms of this like general definition of lifting structure. Okay. And Kahn vibration structure would be the same, but you also have a monomorphism in the vibration.
Okay.
And then to take the push out product.
Yeah.
And then if we apply this to like, and then these counterexamples apply when we do this with a codomain vibration. Okay.
Okay, so the uniformity is sort of built into the formalism. Is that basically what you're saying?
Yeah. Okay. I mean, it's built into the fact that we're using the codomain vibration.
Right. It was okay. So you, yeah. Okay.
And so the appropriate notion of Hom is the local exponentials, and this kind of carries the uniformity implicitly.
Yeah. Okay. Okay.
But we can also work over set index families, and then a family of monomorphisms would be boundary inclusions, if you like, and then okay, and then for actually even then for simplicial sets it's not well behaved, but you can also use Horn inclusions, and then it's fine.
Okay. Yeah. Okay. And is this? I mean, in the paper by Burke and Garner, they also discuss cofibrant generation by a small double category at some point.
Yeah.
Is that something that also fits into your framework?
No, I don't know how to do that.
Okay.
I mean, maybe it does, but it's I think it needs to be, yeah, it's still work to do.
Okay. All right. Okay, those were my questions. Are there more questions?
I suppose I could ask a question.
Okay, go ahead, Jim.
So I'm wondering, you mentioned that local representability sort of meant that we could talk about structures on X in the internal logic of the base category.
Mm-hmm.
And I was wondering if you could give sort of an intuitive idea of why these two things are the same.
Yeah, so I guess if we're working in yeah, so in the internal language of a topos, the only things that we can talk about are things which belong to the topos. So we only have can only talk about a collection of things if it's an object of the topos. We can only talk about a map if it's a morphism in the topos. And so the first thing that definability does is it gives us a representing object of this pre-sheaf. So it gives us an object of B and then a map into the indexing object in in the topos. So this is already, so the fact that we have something, an object inside the topos, is already telling us that we can actually talk about it and refer back to it within the internal language of the topos. And then, so the fact that this is a representing object for the pre-sheaf, this is saying that the thing which is the thing that we have, this object of the topos that we have, is corresponding precisely to the stuff that's going on up in the fibration, which is external to the topos. So I don't know if that helps, but that's the kind of intuition that's
kind of, yeah. So the representing object somehow corresponds to the structure on X, and because the representing object is in the topos, we can talk about it in the internal language.
right. Yeah.
Okay, thanks.
Other questions? No? Then in that case, let's thank Andrew again.
Okay.
Maybe you can stop sharing your screen. Actually, maybe I'll stop the recording. Actually.